natural phenomena that you can see in the board, that butterfly is flapping her wings, or the flower is blooming. These are all natural phenomena and always leads to increase in entropy. This type of phenomena always with an enhancement of entropy. Entropy increases. Whenever this natural phenomena occurs, entropy increases. Now, more the disorderness or chaosness, more is the entropy. Here see the molecules are moving. The movement of the molecule here. The more the molecular movement, more is the entropy. If the volume of the container increases, that also leads to entropy increase. Because it is getting more space for the movement. If the volume is increased for a gas container, that is a container containing certain quantity of gas, if the volume is increased, entropy increases. Because molecules are getting more space. So more degrees of freedom, more movement leads to entropy increase. So these all natural phenomena, whether it is visible or invisible, leads to entropy rise. Blasting of bomb, rising the entropy. All the things, natural or artificial, whenever there is some chaosness, it is increasing the entropy of the system as well as the surrounding. Normally, energy of the system, if increases, the energy of the surrounding is decreased because energy is coming from surrounding to system. So there is a conservation of energy. But regarding entropy, cannot say that. Entropy of the system is increasing, entropy of the surrounding also increasing. That means entropy of the system plus surrounding is not conserved, rather it is enhanced. This entropy change of the system, delta S cis, plus entropy change of the surrounding, delta S star, if you add, it is not zero, rather it is always higher than the earlier. That is the big difference between energy and entropy. Energy is conserved, but entropy is not. Entropy always enhanced. Water freely flowing downwards. That is also here. This is called spontaneous. The water is coming down, is spontaneous process. But if you want to get the water back to the rooftop, you have to use pump. See here. So this is a spontaneous process that is happening by itself. But if you want to get it back, you have to apply certain energy. Freely, it will not go to the rooftop. So these type of processes can be divided into spontaneous and non-spontaneous. Spontaneous processes are happening by itself, but non-spontaneous, you will have to give some effort, give some energy and make it back to the earlier stage. Okay. Carbon plus oxygen, carbon dioxide. This is a natural phenomenon. You are burning some fuel, you are getting carbon dioxide. But can you get back the carbon automatically? No, automatically not possible. So for getting the carbon back, you will have to do the electric discharge in the carbon dioxide. That is some energy. So you have to use certain energy to get back the earlier stage. So this is non-spontaneous. Carbon burning is a spontaneous one, but that carbon dioxide to carbon is non-spontaneous. That you will have to supply energy and get it back. So that is non-spontaneous. Ice is melting to give you water. Okay, now this is spontaneous. But if you want to get the ice back, then you have to keep it in the refrigerator. You have to apply energy to get it back, the frozen one. The molten ice, you have to get it back. The ice slice, if you want to get back, you have to freeze it once again. That means you are supplying energy, not free. So this entropy change dq by t, that is the definition. ds equal to dq r by t. Now this is r for reversible. Now we find it, this r is reversible here. So by definition ds is equal to dq r by t. Now what will be the entropy change for an irreversible state? If you want to find out the entropy change for an irreversible state, why you are not listening? Hey, why are you not listening? You need to listen. If you want to get it irreversible, then what you need to do? All the steps should be reversible except the irreversible one. Make it a cyclic one. What I mean to say, entropy change for irreversible state, if you want to perform, if you want to measure, then you have to make a cyclic process. All the other 3 steps, 4 steps maybe, making a cycle, all the 3 steps, let it be reversible. Then overall the entropy change can be calculated. Now individual steps are also calculated, and if you deduct all the 3 reversible steps from the total, you can get the entropy change for the irreversible process also. Followed me or not? Normally your definition of entropy change is dq reversible by T. Now if you want to make it for irreversible, how do you do it? Because by definition it is reversible. So in that case, what you have to do, you will have to make a cyclic process. In this cyclic process, 3 steps should be reversible and 1 step may be irreversible. Then individually you have to find out the entropy changes of all the 3 steps where it is reversible and overall entropy change. From the overall entropy change, if you deduct the reversible step entropy value changes, then you can find out the entropy change for the irreversible also. That means not directly, but you can get it indirect way. If it is reversible process, you can get it direct. But if it is irreversible, from the cyclic process, you can find out. That is a calculated one. Indirect way can be calculated. Now, if the heat change is happening at different temperatures, then entropy change will be equal to dq1 by T1 plus dqt by T2 plus dq3 by T3 plus dot dot. That way, individual steps at that heat exchange divided by temperature will have to sum up to get the total entropy change. So for irreversible step, as I told you already, so for irreversible, dq reversible here it is reversible. For reversible it is dq reversible minus dw reversible, and for irreversible dq irreversible minus dw irreversible. Now you know that du or de is his internal energy change, and for irreversible as well as reversible it will be same because it is independent of path. Delta E or delta U is path independent state function, that's why. So that's why delta U reversible and delta U irreversible will be same because path independent. That's why we can make an equation like this, and from this way we can find out the entropy change for a irreversible process also. So here, if you follow the steps, it is given in detail and it is shared with you also, so you can find out. So system and surrounding, the entropy change for the system is heat taken by the system divided by temperature, and entropy change for the surrounding is heat released by the system divided by temperature. Okay, so that way you can find out individually the entropy changes for system plus surrounding. But system entropy change plus surrounding entropy change is not 0, it is always greater than 0. It is here, it is given. Just see, calculated. Del S system plus del S surrounding is greater than 0, not equal to 0. Because this Q reversible and Q irreversible, if you compare, Q reversible is always higher, Q reversible by T is higher compared to Q irreversible by T. Okay, because you know work done by reversible process is the maximum. Work done by reversible process is more compared to irreversible process. And entropy change is what? Heat change by temperature. Now work done and heat are directly proportional. So if you take reversible, so Q by T will be higher, and if you take irreversible, Q by T will be lower. So that's why QR by T minus QIR by T will be greater than 0. It is non-zero. Now this entropy change calculation, you know, D equal to dq equal to delta U plus PdV. It can be U, it can be E, depends on books. This symbol can vary. And so dq equal to TdS by second law. So TdS equal to du plus PdV. Divide both sides by T. So you get du here, this relationship. Try to follow, do it yourself. First of all, take dq equal to delta E plus PdV. Write down dq equal to delta E plus PdV. Delta, you can take delta U, you can take delta E as you feel like. Doesn't matter. Some books are following delta U, some books are following delta E. Both are energy, internal energy. Now, next step you write dq, instead of dq, write TdS. First of all, write dq equal to dE plus PdV. Right? Now, divide both sides by T. Right? Next step, this is equal to ds. So integral ds equal to Cv dt by t plus R dv by v. State 1 to state 2. Can't I do it? Try yourself. So delta is equal to Cv ln T2 upon T1 plus R ln V2 upon V1. Is it alright? Up to this? The same thing is written here also on the screen. It is already there. Just see. Instead of dq, we have just replaced TdS. That is second law. Definition of entropy, ds equal to dq by t. So therefore dq equal to TdS. So if you apply that in the first law, TdS equal to this one, du plus PdV. Now if you divide both sides by t, now du equal to Cv dt. If you can take n, you may not take n, doesn't matter. N is for number of mole, and it is a extensive property, that's why it is dependent on amount. So up to this is alright, just check. I have written on the board also, it is there on the PowerPoint also. Same thing. But here I have taken n, here it is n is not taken. Because n is number of mole, and this enthalpy is a entropy. Entropy is extensive property. That means mass dependent property. As entropy is mass dependent property, that's why we may take n. So n is number of mole. So this is the relationship ds equal to ncb dt by t plus nr dv by v. Now if we do the integration, we get del s equal to ncb ln t2 by t1 plus nr ln v2 by v1. Isn't it the same thing? What I have done in the board. Only n is there, otherwise it is same. So this is alright. Up to this is okay. Next step, what you can do, if it is isothermal, then temperature is constant. So this first part will be 0. And we get nr ln v2 upon v1. That is isothermal. Another relationship we can apply, T2 by T1 you replace by P2 V2 by P1 V1. This T2 by T1 you can replace by P2 V2 by P1 V1. P1 V1 by T1 equal to P2 V2 by T2. So here T2 by T1 you can replace by P2 V2 by P1 V1. If you do that, then you get another equation and you can apply other conditions, isobaric and isochoric conditions. If you make it isochoric, volume constant, so this part will be 0 and you get left with this only. Okay, so these are the different ways this can be derived. Based on that, there is numerical here. Follow the numerical. An ideal monatomic gas heated from 300 Kelvin to 1000 Kelvin and the volume is allowed to rise from 22.7 liter to 45.4 liter. What is the change in molar entropy? That formula, based on that same formula. entropy change equal to NCV ln T2 by T1 plus NCV ln V2 by V1. Volume is given, temperature is given. Just apply. The data is all given here. This is the final volume, this is the initial volume, and temperature is also given 1000 and 300. So T2 is 1000, T1 is 300 Kelvin, and initial volume is 22.7 liter, final volume is 45.4 liter. So if you apply, you will get the total entropy change in terms of joule per Kelvin per mole. That is the unit. Entropy unit. This is called entropy unit. Joule per Kelvin. That is the entropy unit. Unit of an entropy is joule per Kelvin. Because what is the formula? Ts equal to dq by t. Q is heat. That can be joule or calorie. So it can be calorie per degree. The unit can be calorie per degree or joule per Kelvin, as you feel like. Both are valid. Okay. So CV is this CV. Last line you see. This CV has come from here. Before that also you check. D equal to NCV reading. No. CV value. Oh, monatomic gas it is told, na? From that it can be calculated. Monatomic gas gamma equal to 1.66. Okay, from there it is CV is there. So 3 by 2. That is told monatomic gas. So from there it is calculated CV as 3 by 2. 3 by 2 R. Cp by Cv equal to gamma equal to 1.66. Cp equal to Cv plus R. So that we can, from there we can find out Cv. R value is 2. What is R value? R is there. Cp by Cv equal to 1. Cv is equal to gamma, 1.66. 1.66 মানে 2 by 3. From here we get C value is coming from there. Because ideal monatomic gas told, from there we can get it. 2 by 3. Gamma equal to 1.6 is actually 2 by 3. So from there we can find out CV value. Because here this relationship is given. Is it okay after this? Or should I wait? Could you understand the numerical here? Bojan? Formula, direct formula. 1.66 actually 2 by 3. 2 by 3. Gamma is 2 by 3. Next is entropy of mixing. Entropy of mixing, we can, I think here you cannot understand, better I will do it. There are two containers. One is the smaller container, one is the larger container. Just for your understanding. This is V1, this is V2, and the pressure initially there is a stopper here. So you can open the stopper so that the gas can freely move. So initially the volume is V1 and finally the another container volume is V2. So total volume is finally, when you open the stopper, it will be V1 plus V2. Okay. Now entropy of mixing, it starts with this value that what is the before and after mixing. We start with this. Isobaric process. We have to complete this one. Isobaric process. So this is one relationship. So isothermal. For isothermal, delta is equal to R ln V2 upon V1. So this particular relationship I am using here for entropy of mixing. What is entropy of mixing? So by the way, this is for 1 mole. If I take n mole, then n will be thoroughly multiplied, nothing else. If I take it for n mole, then n will be multiplied. So initially, number of mole is n1 and here number of mole is n2. Two different gases are there in two different content. Now in between there is a stopper. When I remove the stopper, the gas is mixed together. And I want to find out the entropy change for the process. When it is mixed together, I want to get the entropy change for the process. Now, for the container 1, LS1, inner ln final is V1 plus V2 divided by V1. For the gas 1, for the container 1, and then for the other one, first you tell me whether you understood this or not, because I am using this particular equation. Total volume, final volume by initial volume. Okay, so this particular relationship I am taking here for entropy mixing. Two different containers, we have two different gas. In one number of mole of one gas and into number of mole of another gas. So for container 1, this is the relationship. Entropy change for this container, entropy change for this container. Minus N1 R ln V1 by V1 plus V2. And this is minus into R ln V2 by V1 plus V2. And this is equal to, this V is proportional to number of mole. Any problem? For the container 1, for the gas mixer, one container, second container, two containers separately. Container number 1 and container number 2. So for container number 1, the changes. For container number 2, the changes. Some change is happening when you open it. It is going, this gas is going to the other chamber, and from second chamber the gas is coming in the first chamber. So there are two changes, not one. That's why for container number 1 the change is there. For container number 2 the change is the other one. Now the question is, how can I replace V by N? I am not replacing V by N, but V1 by V1 plus V2 is obviously equal to N1 by N1 plus N2 because N proportional to V. Other parameter remaining constant, V and N will be proportional. Suppose temperature constant, pressure constant, other parameters all constant, then number of mole and volume will be proportional. How? PV equal to NRT. Think over. PV equal to NRT. PT remaining constant. Can't we say that V proportional to N? If the other parameter remaining constant, then V proportional to N. That I have used. Why? Because if I use this relation, then this one is becoming X1. Mole fraction. This is the mole fraction. This is also mole fraction. That advantage I am getting. N1 by N, NR, Ln, X1. equal to minus nr x1 ln x1 plus n2 ln. Now you understand, then only I will open the PowerPoint. It is there in the PowerPoint, but that many pictures cannot be made. Very difficult to draw in the PowerPoint. That's why I am doing in the board, and after that I will show the PowerPoint. Hey, if you cannot understand, ask me. Don't gossip, you talk yourself. Ask me if you have problem. You have two containers, okay. In one container you have got certain gas, that is N1 number of mole, and in another container you have a N2 number of mole of another gas. Now we allow it to mix together. So initially the volume was V1 for the container 1, it is becoming V1 plus V2 as final volume. So final volume by initial volume. And for the container 2 also same thing. Final volume by initial volume. Final volume is V1 plus V2 for both the cases. And for container 1 volume was V1 and for container 2 volume was V2. Now I have just inverted. Usko ulta kiya. Just inverted. That's why becoming minus sign. ln is there, na? Minus sign. Now next step, V1 by V1 plus V2, I make it N1 by N1 plus N2. Because I can convert that into mole fraction. Okay? So we have converted that into mole fraction. Now here, I have divided by N, multiplied by N, no problem. Divided by N, multiplied by N, no problem. So this one is becoming X1 and this is becoming X2. So I have taken minus NR common. NR I have taken common. Inside the bracket it will be Xi, X1 ln X1 plus X2 ln X2. X1 is N1 by N1 plus N2 is X1. N is N1 plus N2 na. Total number of mole N equal to N1 plus N2. Total number of mole N equal to N1 plus N2. And I have divided by N, multiplied by N. So now N1 by N equal to X1, N2 by N is X2. So ultimately we are getting minus NR summation Xi ln Xi. This is the entropy of mixing, the derivation. So the same thing is also there here, okay, but diagram not there, and here you see almost the same thing is calculated, is given in like this, same derivation, only that diagram is not there, otherwise all the same derivation. See here, all these things written, what I drew in the board, same thing is there in the PowerPoint also. You do that practice once more. If you don't understand, then I can do it later also. Do it on your own. This thing, do the practice. And I've done in the board also. If you have any difficulty, you can ask me now, or otherwise you can ask later also. Is it alright? Based on
this is a video about one of the most important, yet least understood, concepts in all of physics. It governs everything from molecular collisions to humongous storms, from the beginning of the universe through its entire evolution to its inevitable end. It may, in fact, determine the direction of time and even be the reason that life exists. To see the confusion around this topic, you need ask only one simple question. What does the Earth get from the sun?
What does the Earth get from sun?
Well, it's light rays.
What do we get from the sun? Later, when Paris is a full energy into useful. If you ran the engine in reverse, first the air expands, lowering the temperature. Then the chamber is brought into contact with the cold bar. The air expands more, drawing in heat from the cold bar. Next, the air is compressed, increasing its temperature. The chamber is placed on top of the hot bar, and the energy of the flywheel is used to return the heat back into the hot bar. However many cycles were run in the forward direction, you could run the same number in reverse, and at the end, everything would return to its original state, with no additional input of energy required. So by running an ideal engine, nothing really changes. You can always undo what you did. So what is the efficiency of this engine? Since it's fully reversible, you might expect the efficiency to be 100%, so no heat would be lost. Of the universe tends to a maximum. In other words, energy spreads out over time. The second law is core to so many phenomena in the world. It's a greater amount, 0.001%.
Okay, I end it here.